Let me call input signal as xit and output signal as xot. So what is the frequency spectrum of the input signal xif? Because we have considered only one impulse, xit can be written as a delta t. Its Fourier transform will be a. The Fourier transform of delta t is simply equal to 1 with respect to f. So xif, the Fourier transform of a delta t, will be equal to simply a. The Fourier transform of x of t. Now how can I write x of t? X of t is nothing but the rectangular function, but it is shifted rectangular function and shifted by amount tau by 2, because original rectangular pulse would have been something between minus tau by 2 to plus tau by 2 with the amplitude of a. So when I shift this rectangular pulse towards right by tau by 2, I get what I've drawn here in pink color. So x of t can be written as the original rectangular pulse is a rect t by tau, because the total width is t, and now I'm shifting the pulse by tau by 2. So that's my original rectangular pulse, and I can write down the frequency spectrum of rectangular pulse as, we know that Fourier transform of rectangular pulse is sinc function, so it is of the form a tau into sinc f tau. But my rectangular pulse is shifted by tau by 2, and hence we will have to multiply this rectangular function with e raised to minus j 2 pi f tau by 2 expression. Why we have to do this? Because this is as a part of time shift property. Later on we will see that this multiplication has no effect on our conclusions. So in frequency spectrum, we have one very important relationship which says that the output spectrum x of f is nothing but the frequency spectrum of the system multiplied by the frequency spectrum of the input signal. So we are right now basically interested in the magnitude spectrum. So if I draw the magnitude spectrum, it will be mod h of f into mod xif. If I take the magnitude of x of f, this is my x of f that we have written here. E raised to minus j into anything will have the magnitude equal to 1. So the overall magnitude of x of f will be only a tau sinc f tau. This is equal to mod h of f into mod xif, that means magnitude of the input spectrum. It is already a constant value, so we will simply write a here. A will cancel out from both the side, and hence the frequency spectrum of the system that we had defined will be of the form sinc f tau. So this is what we were looking for. Now let us see how is this going to help us. We will use this result in drawing of the waveforms in this next slide. We are discussing flat top sampling, please remember that. So let us discuss the frequency spectrum of the flat top sample signal now. The first frequency spectrum that we have drawn is nothing but frequency spectrum of ideally sampled signal. We had already drawn this before when we were deriving Nyquist sampling theorem. It is ideally sampled signal, and you can see the original spectrum, which is between minus fm to plus fm. It repeats around every fs, so we have a repetition around fs, 2fs, and so on. This is frequency axis. This will be fs plus fm, this will be fs minus fm. We are not showing repetition on the negative side, we are just considering it on the positive side. The second thing which I have drawn is nothing but the frequency spectrum of the system which we have considered, h of f, and you can see the magnitude spectrum comes out to be of the nature of sinc function in this case. So this is the frequency spectrum of the system. Now this is my sinc signal. As you can see, there is a main lobe and then there are side lobes. This is nothing but that sinc signal which we have got, sinc f tau, with obviously the constant value of tau, which will decide magnitude at 0. But what we have drawn is a proper sinc function. When I only consider the magnitude spectrum, in that case this negative lobe will become positive. Let h of f be as it is as of now. So the first spectrum is the spectrum of the ideally sampled signal, which we have given name of xif as per our previous discussion. This is my h of f. The third frequency spectrum will be x of f, which will be frequency spectrum of flat top sampled signal. and it will be nothing but multiplication of the first two spectrum as we had written in this case. You can see x of f is nothing but multiplication of h of f and the input frequency spectrum. So let us now multiply the first two spectrum and see what we get.